Napkin. Shorts and cowboy. And
Did you lose your math?
over the shoe. Yeah. That's just a no-no.
I tried to tell them. I put it on his tab.
He wants his alternative.
So he pulls up his socks over his pants.
Mr. All, can I go in a room?
Sure. All right. We're gonna go over a couple examples, then we'll just have some work time. I think maybe going over 3 examples should suffice. Look at that guy.
Well, that's square plus 2.
What kind of function,
Oh, no.
just by himself, what kind of function is this guy? Yeah. All right, guys, quiet down. This is an even function, and it's being added to. What kind of function is he? Another even function. So even plus even. Let's plug in a number to be sure. It seems like you plug in a negative number, won't the squaring things kind of turn them positive? So plugging in a negative should be equivalent to plugging in the corresponding positive value. So anyway, how about, who knows, 2, sure. Plug in 2, you get 4 plus a quarter. So 4 1/4. If you plug in negative 2, lo and behold, the square and the square turn them both positive, and you get the same exact number. So this tells us that the function is
Sick nasty.
it's sick nasty, exactly. It's even. Okay. All right, now to graph it. This one, you got to be a little maybe a little think on your feet here, I guess, because you got to think about how this function would look like this. And this function would look like this. So what happens if you add them together?
Oh.
Hybrid. You got the things on the sides, and that's in the
They
middle.
look like
Those
two
are on the
parabolas.
sides.
Yeah, so what's gonna happen is for small x values, so let's say x values like 0.01, number like that. Which of these terms would be bigger if we plugged in 0.01? This one. If you plug in 0.01, well, this guy's gonna be tiny, right? 0.01 squared is a 10,000, very small number. But if you plug it in here, it's 1 over a 10,000, which is gonna be a huge number. So what that tells us is that for small x values, this behavior dominates the function. So for small values, we get these asymptotes. But then for large values, let's say we plug in 100. Well, if you plug in 100, now this number is really small, and this number would be 10,000, which means that for large x values, there's that kind of behavior. Okay, so again, for small numbers, you get this asymptotic behavior, and for large x values, you get this type of parabolic end behavior. So what that looks like would be, well, these aren't parabolas, but almost. Although it's worth pointing out that if you looked over here, if you zoomed in on that part of the function, it would look pretty parabolic. It would have, because the end behavior is, as x gets large, this term dominates. So for large x values, there'd be, you look at that, you go, oh, that's awfully close to a parabola. For very small values, you look over here and say, wow, this function looks a lot like 1 over x squared. So there you go. I like to think of this kind of as like, it's a parabola. Can you see the parabola shape kind of? He kind of like inherited the asymptote from the 1 over x squared.
He is W.
All right, how do you feel about that, guys? Cool. I want to go over 11 and 12 because they look so similar. They're not. They have some similarities.
They took
Don't get TikToked.
too late.
It's too late.
I'm so mournful. I sounded so distressed.
He sounded dare I say, sad. Sad. All right. Look at those. Let's start with, I don't know, maybe you guys can tell me, which one do you think is going to be easier to think about? Well, this one's easier? I would agree with that. So looking at the top, are there any issues that concern us about, so speaking about domain, are there any numbers that might cause issues with this top thing here? Because for square roots, what can you not square root? Negative numbers. Can this thing ever be negative?
Yeah.
X could be negative, but can the thing we're taking the square root of, this x squared plus 1, can that ever go negative? Is it possible? No. So that's nice because you go, oh, that actually makes things easier. Because this top, I don't have to worry about it. But the bottom tells me that x cannot be 0. That's the only number that's a problem. Okay, so let's look at the graph here. Let's get some end behavior. By the way, when you have this, that means the graph can never have what item?
A
Y-intercept. So right off the bat, we know there's no y-intercept. And the fact that this is the only number that can't go in, that's a big hint that there's going to be a vertical asymptote at 0. All right, here's where it gets interesting. As x approaches infinity, does anyone think they know the answer to this one?
Plug in big X.
The answer is 1. And yeah, that's one way to always, you can always come back to that is, say x was 100. And ignore the 1 because 1's so tiny compared to 100 squared, so I'm just going to ignore him. 100 squared square rooted is 100. So if you were to plug in 100 for your x, you'd have 100 over 100, which is going to be that one. Also, you could look at this and say, if I cover up the 1, I have square root of x squared over x. What's the square root of x squared?
That's X.
Sorta. It's actually the absolute value of x. Actually. Well, do you see why this would matter for negatives? So if x is positive, sure. If you know x is positive, then x squared square rooted is just x. But if x is negative, so say x was negative 10. You'd go negative 10 squared, 100, square root 10. So if you think about what happened there, is if you plug in a negative number, you actually end up with the absolute value, the positive version of that number. So this is something good to keep in mind here. The upshot of that is, if x is going to negative infinity, what are my y values going to approach then?
-1.
-1. Is everyone cool with that idea? All right, so this graph has 2 horizontal asymptotes then. Ooh, there's a horizontal asymptote over here on the right. And there's a horizontal asymptote. You can draw it all the way across if you want. I mean, the asymptotes aren't actually part of the function, so as long as you're making it clear that, hey, this curve I'm going to draw is approaching this flat line, then you're fine. I kind of like this because it just reminds me that this is only the right side end behavior. All right, so what do I do? What next? By the way, we kind of skipped over something, but this right there is pretty good evidence that it's going to be an odd function. We can always check. I mean, it'll take 2 seconds. Oh, that's a good number. I don't know. 4. 4 would get me root 17 over 4, and -4 would get me negative root 17 over 4. Okay, great. It's an odd function. All right. So, is the next step? How do we feel about the next step here? Does it make sense how there's really not, there's not much freedom here as far as, can I go negative over here? No. I just have to approach the asymptote, approach the asymptote. So this function ends up having a very bizarre range, if you think about it. The range is, what kind of y values does this function hit? One, every number above 1 and every number below -1, but it misses every y value between -1 and 1. Do we understand that? I like your mustache mask, Seth. It's beautiful. Very, very lit. All right, 11 will be more interesting, maybe not. All right, 11. Hopefully you look at 11 and go, well, I mean, there's a lot of similarities between this and this. Someone throw out one big similarity between this and this. The end behaviors are going to be the same, right? If I cover up the non-dominant term, it's the same end behavior. The domain's not the same. How about, you see negative, Taylor? Is that you? Do you say the negative numbers? Negative eyes?
Yeah.
It's ventriloquism. I can't tell who's talking. But anyway, yeah, if you look at if you think about plugging in a positive versus a negative, this function's also going to be odd. It's another similarity. The big difference is the domain. That's the huge difference. So why is that so different? Well, you still can't plug in 0. That should be fairly clear. But yeah, well now, let's not think number by number, but I guess I contradict myself, but do you guys see why I couldn't plug in a number like 1/2 anymore?
Yeah, because you'll have a negative.
Very good. You try to plug 1/2 in there, 1/2 squared minus 1 is a negative number. But you can't take the square root of negative numbers. So we obviously have to resolve that, right? So let's go over here and say, what has to be true about this x squared minus 1?
Bigger than 1 and smaller than -1. It has to be a whole number.
What?
I mean, a whole number of the sides of the book.
You're getting ahead of us here. I'm just asking the thing under the square. So if you have, but what you said was actually correct about you actually have the correct domain, but you're just a little ahead of where I'm trying to go here. So I'm trying to explain how, if you have the square root of something, in order for this to work, the thing has to be positive or 0. Does everyone understand that? Okay. So this must be greater than or equal to 0. So then let's think about that. So you talked about 1 and -1. So am I safe to say that's obvious that 1 and -1 are the two numbers that make this equal to 0?
Yeah.
Okay. Now, what if x was bigger than 1? What if x was like 7? Any number bigger than 1, does this work?
Yeah.
Happy.
Yay.
Yay. How about if a number was like -7?
Good. Okay.
But if you were between -1 and 1, no. Sad.
Mad.
All right. So what this means is that every number 1 and bigger, and every number -1 and less is okay. By the way, does 1.1 work? Yeah. 1.01? Yes. Does 1 itself work? Yes. 1 actually. What do we actually put this on our graph right now. If you actually plug in the number 1, no. If you plug in 1, you'd get 0 on top, 1 on bottom, which is 0. Same thing with -1. So those are both x-intercepts.
Yo.
So let's write our domain notation. Boring part, but it's important to have correct notation. So the domain would be any x value to the left of or at -1. So x value is less than or equal to -1, or x value is greater than or equal to positive. Everyone's okay with this notation, right? Mr. Alligator, eat the bigger number. Or I should say the greater number. Okay, so there's our domain. The end behavior is the same as this one. So end behavior would be as x approaches infinity, y approaches 1. All right. Can you visualize it?
Yes.
Do you see it? Put these asymptotes in here. Okay, don't overthink it. What point has to live on my graph? This one. And what do I have to do as I go to the right?
Get closer.
I got to approach this line, so let's just do that. Okay. On the left-hand side, I have to also follow a similar pattern. So, by the way, does anything get graphed in here between -1 and 1? No, it's not in the domain. No man's land. Okay, so
Yeah, I don't like this function.
why not?
It looks funky. It looks.
Oh, it doesn't?
I don't like it. It looks like funky.
Interesting range here. The range is all numbers between -1 and
It's
+1,
the opposite range of the last.
in a sense. Although neither range includes the number 1.
Yeah.
So they're pretty close to being what they call complement sets, but almost. Huh? Yeah, because this one, the range would be all numbers greater than 1 and less than 1, -1. So neither function actually produces a y value equal to 1. All right. Should we do one more together?
Yes.
Yes.
We'll do 15 together.
Leave me to my own thing.
15 is very weird.
Be sure.
This will be the last one we do on video, I guess, today, and then we'll have some work time. Who can be super brave and throw an answer out for why is 15? What makes this one way different than every previous function on this page? But Alyssa, you got an answer?
It's f of x.
That's an answer. Not what I'm looking for. Anyone else? That's something, yeah. It has a minus x squared, which none of these other ones, I think, really have that. 7 has a minus x squared, but in a different way. I'll give you a hint. It does not really have blank. Doesn't really have. Yeah, very good. Does not really have end behavior. Yes, because can x go to infinity? Can x be big?
Oh, that can't be the
X can't even be like 5. Plug in 5, it doesn't work.
X can at most be 3.
Yeah, so if I make a number line and ask, what numbers are okay? This is my domain line. Well, I like that you throw out 3 there, right? 3 is sort of this number that would make the inside 0. And x can be bigger than 3, but so -3 would also make the inside 0. So if you think about it, really it's just numbers between -3 and 3. Does everyone understand why that is the case?
Yeah.
Why x can't be like 4? Why x can't be 3.2? You sure?
Yes.
Okay. So the domain is a strange, like very limited interval. It's only x values. What's going on over there, Hunter? Let's not do that, please. Thanks. Okay, so there's my domain. That's one way you can write it. The last time we did, the domain was kind of an or. It was x has to be bigger than or equal to 1 or less than or equal to -1. Whereas this one, it's x must be greater than or equal to -3 and also less than or equal to 3. It's kind of a subtle difference, but do you guys know what it would look like if you said this? X is greater than or equal to -3, or X is less than or equal to 3. How many numbers qualify for that? Every number, right? Think of the 17.
Yeah.
Is 17 bigger than or equal to -3 or less than or equal to 3? Yeah, that satisfies that one. So if you did this, it would actually include every number. Well, that gets into some logical stuff that some of you guys might not sit right with you. If I say true or false, AJ is a human or
False.
AJ is a lizard.
I mean,
That is true. To be true, only one has to be true.
probably Mark Zuckerberg.
True or false? We live on Earth or Mars. True.
I think it's false, actually.
True or false? We live on Earth and Mars. That is false.
We live in a simulation.
Oh,
Yeah.
right. Simulation. Yeah.
Man, I need to restart my character release.
All right. So what happens if you actually plug in 3? You get 0. So here's 3. There's 0. Plug in -3. You also get 0. What's the other number I might want to plug into this?
0,
How about plugging in 0? Plug in 0, what do you get? 3. Now the question is, well, I don't know, does the curve go wheel? Or does it look like sombrero? How does it look?
It looked like that.
This is a good one where I think once you understood the basics, it's a good one to look at a computer. Mr. Computer will tell you that the shape looks like this.
No, it's
It's a
fair.
rainbow.
That's right, I know it's
Okay, which hopefully raises the question:
Why?
is that half a circle?
No, it's a rainbow.
Because it doesn't have to be. I mean, certainly you could have a curve that does this. I mean, some kind of rounded structure that hits those 3 points and isn't actually a circle. There's a lot of stuff like this in math where some structure looks like, it looks kind of like an ellipse or a circle, but it's not. But I'll show you real quick. It is indeed half a circle. This is kind of a little bit beyond what we're covering, but you might recognize this as being the equation of a circle back from like geometry maybe or algebra. If I rearrange this, a little bit of algebra, take square roots.
It's, whoa.
Now notice, to get the entire circle structure, I have to go plus or minus. That gets me the plus and the minus side. If I don't have the minus side, I just get the positive y values on the circle. And there you go. So this is indeed a half circle. This is actually a famous calculus problem because in calculus you learned about like you get some function and you calculate the area trapped between that function and the x-axis. Anyway. This one is like notoriously difficult to try to calculate it, but if it's like a trick question. If the person recognizes, it's half circle, you can calculate the area very easily. Okay, I'm done. Okay.